All right, so welcome to the first video of the modeling section. So if you open up your model.py file, it should look something like this. So the only thing new here is hopefully you guys have scikit-learn and Keras installed already. And the big kicker is hopefully you have TensorFlow GPU installed, because the GPU version just makes everything so much faster when we get around to actually training our models. Okay. Again, this whole tutorial is a little more advanced. I'd be pretty surprised if this is your first time doing deep learning, but you're gonna have to take some time to set up TensorFlow and get all this stuff installed if you've never done it before. So that could be kind of tricky, but good luck if you're trying to do that. And so this portion of code is directly from the eda.py file. So this should look really familiar. This is just creating that pie chart for the class distribution that we talked about before. And the only thing that's changed is we're actually reading from the clean directory, right? Because we downsampled our audio, and then we also removed the dead spots in the audio as well. So we did like noise floor detection. And so if you run this now, you'll see that our class distribution looks pretty similar, but you notice like bass drum went down by 1%. So we've removed a little bit of data here and there, but the whole point of the modeling section is I want to start talking about how we handle class imbalance when we train a neural network. So to get started, this whole video is going to be about, like, we're going to make one function, and that function is going to create our X matrix and our Y matrix. So all of our little samples of audio with their corresponding classes, okay? And how are we going to do this? Well, audio is a little different from most data because it's being sampled so frequently, and you have to create like an arbitrary length of time that you want to actually build a sample with. So I'm only going to use 1/10 of a second of audio for each sample, which is very small. Like, you could use a second if you want. I wouldn't go any higher than a second, but I think it's very impressive if you only use like 1/10 of a second, which means in real time, your model would be able to very quickly discern like different classifications, like extremely quickly, which is pretty interesting. But the way we're going to do this is we're going to randomly sample along the length of our audio files, and then we're just going to take that 1 second chunk out of that audio. And so in order to do this, we're going to create, or first we need to establish how many samples are actually possible within our signal. So if we just move through an audio file and we just keep like chunking it bit by bit, you would move forward every 1/10 of a second. In order to make this a little bit, like, to increase our sample size, I'm going to say n samples is going to be equal to twice that value. So let me just set it up for you guys. I'm going to take the integer, and if you remember from before, we had this length column. So if you take the length, where did I go? You can take the length, and you can calculate the sum of all the values in the length column, so you can get the total length, and then you can divide by 0.1. So we're only going to be looking at, all right, sorry, we should put this division here. So we're going to divide by 0.1, so that's 1/10 of a second. So this is saying, like, what's the total length in seconds of all of my data, and then what happens when we actually divide that into 1/10 of a second chunks. And then I think the number for that is like right around 13,000. And what I'm doing is say I want to take a step further. I want to take twice that number of samples that you're going to be drawing from our population, just to make sure we have enough data. So now let's create a probability distribution. The reason we're creating a probability distribution for our, like, so we already have kind of the distribution defined, but we need to create actual, like, we need to convert those into values between, like, that will all add up to 1. And the way we can do that is we'll take our class dist that we already solved for before, and we're going to just divide this by class dist dot sum. So that'll convert everything between 0 and 1. And then, I don't know. This is how we're going to be doing the random sampling from our audio data. We're going to do choices equals numpy dot random dot choice, I believe. Okay. So with choice, we're going to give it a class distribution dot index. So this would be all of our different musical instruments that we have to choose from. And then we can also generate the way we make that decision is we base it off of the probability distribution that we already created. So if I go ahead and run that, choices, so it just ran once, but it randomly went to saxophone. See if we can get something else. We run again, cello. So it's just randomly sampling based on this probability distribution. And our prob distribution looks like this, just so you guys know. Again, here's our index. And so we only have like a 2% chance of actually drawing from bass drum. That's what this would mean. Okay? So now we're going to create, let's actually create our configuration, which this is gonna come in handy later on. So this is gonna be a class, I'm gonna call it config. And we're gonna initialize it with a bunch of constants that we want. So if I want to change some numbers like in my model down the road, I can just change it in one spot and it'll just affect everything, which is what I want. So that's why we're creating the config class. And so there's going to be two modes that our models are going to run in, convolution and recursion. So, or I guess recurrent. Why did I put mode equals? So mode is going to equal to conv. And if you remember with some of the stuff we did, we had to define the number of filters. That's still going to be 26. We have to do n features, so n feet is going to be equal to 13. So that's the number of MFCC coefficients. And NFFT, so before NFFT was what, 1,103. Now it's going to be 512. And the reason for that is that our rate has been downsampled. So if you go back to the original PowerPoint slide that I showed, this was the number of FFT. So like the window size gives you 400 points, and to fill that out, it's going to add 112 zeros onto that to reach this 2 to the, I don't know what power that is, but this 512 is a power of 2. So that's why we set the num FFT to 512. Because our window size actually takes in 400 points with a sample rate of 16K. So now let's just go ahead and set all these values. So self.mode, nfilt equals nfilt, nfeet equals nfeet, rate equals rate, and self.step equals, okay, so this other one is the steps. So this is the how much, like, well, this is 1/10 of a second. It's how much data we actually compute when we create our window size, which is going to be 1/10 of a second. So I just called it step. And let's see, I think let's go down here and let's call config. So config would just be equal to this initialization, and I think I'll just set the mode to convolution for now. See if that runs okay. Cool. All right. So no, at this point, like I said, we're going to run with either a convolutional neural net or a recurrent neural net. So the main difference between these two is the shape of what the data is going to have to be in when we put it through the model. So we need to check the mode that we're going to run in. So if it runs in convolution, we're going to have, let me see if I can put some more spaces here so you guys, there we go. So, and what we're going to create this whole, we haven't even got to it yet, but it's called build ran feet. Okay, so this is just going to build our feature set from this random sampling that we talked about with numpy random.choice. Okay, and I guess because let's actually go down here. So we'll say else if config.mode equals, I just called it time. You call it whatever you want, and this will build out a slightly different bit of data that's also going to be spit out from this build random feet function that we'll build here. So at this point, let's see if that runs. Oh, of course. Okay, so let's actually make the function that's going to build all of our data, so it'll be pre-processed to push through our models. This is going to be a rather big function, but it's actually not that bad. The more you do this stuff, like, the easier it gets. But if you're confused, I would not be surprised. So let's start with, I'm going to make two lists, X and Y. And the reason for that is just easier to do this stuff in lists and then convert it to a NumPy array later. So we're going to have a min and a max. So in order to figure out the scalings, sometimes you can just do like a min max scalar and like figure out what, like, how you're going to normalize your values later on. But because of the shape of these neural networks, I kind of have to do it this way. Min max. So I'm actually going to initialize min to the highest value that float can take on, and then I'm going to initialize max to the lowest value just to make sure that these get updated. And what we're going to do, and the reason why we're going to track the minimum and maximum is that for neural networks, typically you want to normalize your input between 0 and 1. So we're going to need to know what those min-max values are. So let's get started with for blank in TQDM. We don't actually care about what we're iterating over. We just want to go through the range of our number of samples that we set from before. And let's start by generating a random class. So first I will say, okay, well, I want a random class that, again, follows with that probability distribution we talked about before. And so that's going to be class dis index, because I want to get a random musical instrument. And our probability is going to be equal to our probability distribution. So now we're going to generate that file. So there's another element of randomness within the actual file that we pick. So we're going to do, and you don't technically have to do this, but there's another way to do it, but this is probably the best. So now we actually have to go in and pick a random file based on the class that we had just allocated. So if you remember from before, the way we did this is we checked the label and we check to see if it equals the class that we just randomly picked from, okay? And we can get the index. So if you remember the index, I believe, I wonder if I ever reset it. The index should be, yep, it's the file name. So I guess I didn't change that. I moved it into the index. So again, the file name was set to the index. So when you take this dot index, that's going to produce the file belonging to that class. All right. So now that we've randomly generated a file name, let's go ahead and read it in. So we're going to say rate and wave is equal to wavefile.read, and we're going to read into our clean directory for that file. And we're going to say now we have to get the labels. So technically we don't know, maybe we do know what the label is. Oh, anyway, let's just do dataframe.at. So again, we're going to index at the file name for this specific label. I don't know why I did that, because it's probably right here. And now we're going to get a random index. So this is where we start to randomly take just a value based on the length of our audio file, and then we say I just want to sample right at this index, and then take everything for 1/10 of a second after that index, and that'll be my X distribution that will pair with this label that we already created. So we're going to do a numpy dot random integer. So we want to pull a random integer from the start of this file to wave.shape0, so the length of it, but we want to subtract off config.step. So config.step, if you remember, was that 1/10 of a second, to make sure that we don't like go to the end of the file and then run out of data points. We're just gonna stop at that's why we take this negative, or I guess minus config.step. Okay, that looks good. So our sample, we're going to take a random sample from our wave file, and it's going to be based on our random index that we just generated from before. And we're going to go from random index to ran index plus config.step. So this is just saying, well, I want to index from my random index, I want to go 1/10 of a second from that, and that's how I'll get my actual sample that I want to compute with later. So now we can create one sample that's going to go into our matrix. We'll call it X sample, and this is where we actually calculate our MFCC coefficient like we did in the last video. So we'll take sample and we'll give it a rate. So the arguments for this are num_sep, which is going to be equal to config.endFeet. So that's the number of MFCC coefficients that I want. And those are going to be calculated based on the filter bank energies that come from config.endFilt. Okay, so that's 26. And then NFFT is just equal to config.nfft, right? Or, ooh, endFilt? Wait, did I not? Let me go down here. Filt, feet, rate. Okay, so self.n, maybe I just forgot that, equals NFFT. All right, so there we go. And hopefully that looks good. This is getting really, oh well. And so in order to have this shaped properly, we're just going to do a transpose. Just trust me on that. So the next thing to do is we need to update our min and max. So it's going to be like a running minimum. And the way we do that and the why we initialize those values is we do numpy min, or I guess, oh, the way this works, a min. So a min lets you take like an entire matrix and push it in there, and it'll just grab that minimum value from that matrix, and we'll just check that against our existing minimum. It's like, do we have a new minimum? All right, let's update it, and then we'll create a maximum, which will be just the max of numpy.amax of X sample max. Okay, that looks good. So now we can add our sample into our actual list. So we'll do x.append, and this is tricky. This has to do with the shape of how the data goes in and eventually works for like which model it's going to build through. And you might want to check this yourself just to make sure that you understand the shape of a lot of this data. But what we're going to say is we're going to append X sample. So we're going to append our sample as is if config.mode is equal to convolution. So if we're building out the convolutional neural network, this is what we're going to use. And if not, we're going to build X sample dot transpose. So it's a simple matter, and if you don't understand this, I'll explain it when we actually get to building the models. And then now we're going to do a y.append. That looks good. Classes, let's see, classes.index of label. Okay, so what we're doing here is, if you remember, like, if I have this over here, classes. So classes will have an index, and this is the actual, we need to go from our strings and we need to encode them into integer labels. The way we do that is we say, well, I've got classes, I want to take the index of that, and I just want to get that index for this specific label. So we're going from a string, our string label, and going and encoding them into values between 0 and 9 for our neural network. Okay. So at that point, we've gone through all of our data, we've built it out, and we can create the NumPy arrays. So we'll just convert both of these. We'll create X into a NumPy array, and Y is going to be a NumPy array. So that's good. And now we can normalize X. So we just kept track of all those min-max values, and we can rescale it between 0 and 1. So the way you do this is just this. You can stop and think about it a little bit, why this actually normalizes your values, but I think that looks good. All right. So at this point, we need to reshape our like, I guess our NumPy array for X, X and Y a little bit. So, and this is just because I'm trying to run convolution and like a recurrent neural network and making that data build out from one function. So that's why this is so weird, but it works out. So if we're building a convolutional neural network, we're going to need to reshape X. And the way we're going to reshape this is it goes from X dot shape 0, X dot shape 1, X dot shape 2. And so it's pretty much everything, but we need this 1 here. And the reason we need this 1 for convolution is you can think of that whole matrix, and it just has like a one-dimensional like grayscale pixel, and that's what we need to create right here. So this is like n samples by, I'm not sure because I did this transpose here, but this will be like, I think it's 13 by 9. Oh, maybe it's 9 by 13, something like that. We'll see that later, so don't worry about too much. But else if config mode equals time, so we're building out the recurrent neural network. The recurrent network is pretty much the same, but we just don't have to do that weird, we don't have to add that 1 at the end. So that will be good. That looks good. So now we've reshaped this, and this is the last step. We need to talk about converting to, so because when you do the cost function for these neural networks, you'll have something called like categorical cross entropy. And in order to get this, like, so right now we've got, what do we got? Classes between 0 and 9. We need to take these 0 and 9s and like hot encode them into a matrix. So like this, the first element of this matrix, if it's 0, is going to be 1. Whereas if it's 9, the 10th element of that one part of the matrix is going to be equal to 1. So it's just hot encoding your linear variables of y. So we have to give it the original y, and then we have to also give it num classes, which is going to be equal to 10. Okay, and then just return x and y. And now that's it. We've completely shaped our data. It actually takes quite a bit of time to build out. Let me see if it builds. Cool, it actually worked. So look, it's making 26,000 samples from our population, which is like all of our audio data. It takes quite a bit of time to run, but this should work, should be running. I think I'll talk about the shape of this data in the next video because this has gone like way too long. But in the next video, we'll be ready to put our data through the neural networks, and it'll be, hopefully everything will pay off. Like usually 10 or 20% of your time is actually working with the neural networks themselves. So yeah, the dimensions of the convolution was 13 by 9 by 1. So looks good. So hopefully that wasn't too painful. I know this is like extremely confusing what I did here, but if you take the time to actually like figure out what's going on in terms of dimensions and how we eventually wind up with like this 4D matrix, it'll pay off in the end. You'll actually learn something, and that'll be good. So in the next video, we'll start the modeling.